My name is Oktay. Welcome to today's video about the chemical element iodine. This is a picture of the element iodine as crystals. It has the atomic number 53. Its name comes from the Greek word iodis, which means violet colored. And it is in nature as an iodide and iodate ion IO3-. The main isotope is the isotope 127 with 100%, and there are traces of the radioactive isotope 129, which has a half-life of 15.7 million years. This is a picture of the periodic table. Iodine is here. It is a member of the halogen group, salt maker, and it is located near the metals, and it's an essential element. The origin of iodine is from dying low-mass stars and merging neutron stars. This is a picture of the abundance of the chemical elements in the Earth's crust. Iodine abundance is about 0.05 parts per million. Iodine is here. However, it is assimilated in seaweeds. This is a diagram of the electronegativity of the chemical elements, and iodine has a lower electronegativity than fluorine, or chlorine, or bromine, but it is still very reactive. This is how iodine was discovered by French chemist Bernard Courtois in 1811. He discovered it from seaweed when he treated seaweed ashes with sulfuric acid, and he saw a violet gas and a violet substance, and that was iodine. These are three examples of iodine minerals. At the left, that's iodide, AgI. In the middle, it's meersite, which is the yellow, that's meersite, which is silver copper iodide, and at the right, that's marshite, which is a copper iodide. There's another picture of iodine crystals. It is produced by extracting it from brines. Brines are concentrated salt solutions. This is the chemical reaction. 2 hydrogen iodide plus chlorine gives you iodine plus 2 hydrogen chloride. This is a picture of an iodine mine in Atacama Desert in Chile. These blue areas are evaporation ponds, and the iodine is isolated from the brines. The world production in 2021 was 32,000 metric tons. Number 1 producer was Chile, number 2 was Japan. This is a comparison of 3 halogens. At the left, that's greenish yellow gas, that's chlorine. In the middle, that's a reddish brown liquid, bromine. And iodine, I2, is a violet solid. That's at the right. This is a picture of iodized salt. As an example, in Switzerland, 25 milligram iodine was added per kilogram to salt in 2014. And this makes a lot of sense because it is an essential element. The human body has a reserve of about 15 to 20 milligrams of iodine, and 70 to 80% of this iodine is located in the thyroid gland. This is how the thyroid system works. It is controlled by the gland and the hypothalamus in the brain. And these two hormones, T3 and T4, play an important role. They control the metabolism, the growth, development, but also stimulate body heat generation. And catecholamines are stress response hormones. And you can see in the picture, this is a feedback system controlled by the thyroid gland and by the hypothalamus. This is at the left the structure of the molecules T3 and T4. T3 is triiodoscyronine, and at the bottom T4, that's S-thyroxine. The difference is T4 has one more iodine at this position, and T3 has just a hydrogen atom. And those two hormones control nearly every cell in the body. There are three reasons why fish is very healthy and a superfood. This is called in Bavaria Steckerlfisch, that's grilled fish on a sticks. Number one reason is it's a great protein source because it contains essential amino acids. Number two is it is a very valuable fat source because it contains the polyunsaturated fatty acids like linolenic acid. And number three reason it's a very good source for iodine. Spinach, milk, and eggs are also a very good iodine source. This is how you can test iodide with a solution of silver nitrate. This gives you a bright yellow precipitate. The reason is the high lattice energy of silver iodide. This is in the picture on the right, that's silver iodide, bright yellow. In the middle, that's pale yellow silver bromide, and at the left, white, that's silver chloride. And this is the chemical reaction. Sodium iodide plus silver nitrate gives you silver iodide precipitate plus sodium nitrate. This is another test for iodine. That's the iodine starch complex. It was discovered in 1814, and this complex has a blue color. The triiodide ions are important in this complex. They go into the spiral. Spiral is made by the amylose, which is one of two components of starch. The other component is amylopectin. And this is called a charge transfer complex because it's an electron donor acceptor complex. The amylose is the electron donor and the triiodide is the electron acceptor. This is more complicated because iodide tends to make bigger ions, like for example I4 2 minus, I5 minus, up to I29 3 minus. This is what you can use the starch test for. At the left, that's a slice of apple, and you can treat it with iodine and iodide to determine the correct time for harvesting. At the right, that's the 3D structure of amylose, and you can again see the importance of these dotted lines. These are the intermolecular hydrogen bonds that give this molecule its 3D structure. This is a picture of olive oil in water. You can use iodine to determine the percentage of the unsaturated fatty acids. This is called iodine value. This is defined as the grams of iodine that are consumed by 100 grams of a substance. And the iodine is added to the double bonds. With an iodometric titration, you can determine the amount of used iodine. And examples are coconut oil has an iodine value of 6 to 11, olive oil 75 to 94. This means coconut oil has a high percentage of saturated fats, and olive oil has a higher percentage of unsaturated fatty acids. This is the compound hydrogen iodide, HI. Its 48 to 57% aqueous solution is called hydroiodic acid. It's a very strong acid because it has a high bond length, and the bond is very weak. So the molecule can get rid of the proton very easily. And at the left, that's the Cativa process. This is a process to make acetic acid of methanol. This is how it works. The methanol enters the cycle here. You get iodomethane, which adds to this iridium complex. Then one of the iodide ions is replaced by carbon monoxide. You get this intermediate complex number 3. In this step to number 4, this is where the carbon monoxide goes between the iridium ion and the methyl group. This is where the new carbon-carbon bond is made. And at the end of the circle, you get a molecule acetic acid. And you get your catalyst back. And this is a picture of the compound Iodoform, CHI3. It was first produced in 1822 by Georges Simon Cerulat. It is a natural product. It can be found in fungus Angel's bonnet. And Iodoform is used in dental medicine for disinfection. These are two compounds of iodine with oxygen. At the top, that's iodine pentoxide, I2O5, which is an oxidant for carbon monoxide, which is important for the analytical chemistry. This is the reaction. 5 carbon monoxide plus iodine pentoxide gives you iodine plus 5 CO2, carbon dioxide. At the bottom, it's this periodic acid, HiO4 or H5IO6. It can be used for the Malaprade oxidation, which is a glycol cleavage reaction. That oxidation of this diol component is periodic acid, which gives you this intermediate compound, which then splits into 2 carbonyl compounds. So in this reaction, carbon is oxidated and the iodine is reduced. At the left, that's an ionic drive with electric propulsion, like it was used in the spacecraft Deep Space One. It used xenon as a fuel. This engine gives you a weak but a continuous thrust, and over time the Deep Space One spacecraft reached a very high velocity. And iodine can also be used as an alternative fuel to xenon, because both these elements are very heavy, and that is what you need for this type of drive. At the right is a picture how this drive works. The fuel is ionized here, and then accelerated by a magnetic field. And this gives you this thrust for the engine. This is a picture of potassium iodide, Ki. This is in the World Health Organization's list of essential medicines. You need about 130 milligrams per day for protection against radioactive 131 iodine, which has a half-life of 8 days. So the trick is to saturate the body with non-radioactive normal iodine. Then the iodine 131 is not assimilated, but it's practically rejected. And this is how it works. And half-life of 8 days means after, in case of a fallout with iodine 131, after a few weeks, most of it will be gone. These are 2 examples of iodine in medicine. At the top, that's the compound diazoic acid, which is a contrast agent for X-ray imaging. And the radioactive isotope 131 iodine can be used for treatment of thyroid cancer. It has a half-life of 8 days. It decays to xenon 131, and it emits a beta particle, which is a fast electron, and the fast electrons kill the cancer cells. A picture of a nice meteorite. There's another radioactive isotope 129 iodine. It has a half-life of 15.7 million years. Its practically only source is supernovas. And in some meteorites, there was an overabundance of the isotope 129 xenon. And this is very interesting because it gives us a glimpse into the very early stage of the formation of the solar system, because it means that the supernova and the solidification of the gas cloud happened very quickly in the early solar system. And yeah, this is very interesting and gives us It's like you're traveling back to the time when the solar system was formed. And it could very well be that it was this supernova which triggered the formation of the solar system. This interesting reaction is called elephant toothpaste reaction. It's the reaction with hydrogen peroxide with potassium iodide. Iodide works as a catalyst. I hope this works. And this is a disproportionation reaction. The hydrogen peroxide is oxidated and reduced at the same time. And the oxygen gas makes this foam. This is a nice picture of iodine crystals. That was today's video about the chemical element iodine. Thank you for watching. Have a nice day. Bye bye.